So we're looking at definite integrals and how to actually go in and solve these things, right? We've talked a lot about properties. We spent a whole lot of time talking about what these things actually tell us. But now it's time to go in and like do one, right? Evaluate one and tell what this thing's equal to. So we're going to be using the fundamental theorem of calculus. There are two parts to this fundamental theorem, and we're going to be looking at part two. All right, and so then in the next section we go in and we look at part one. I know that seems kind of weird. Why would we do it in that order? The reason being is that part two, the fundamental theorem part two, is really the application side of it. It's what you're going to see the most of. Part one is kind of a special case, and we'll look at that and talk about it when we get there. So here it says use the fundamental theorem of calculus part two to evaluate this integral. Now we've talked about this, right? And we said, hey, these are the consequences of it, but we haven't actually gone in and done a problem. But what we did establish was that when we talked about net change, we talked about all these other things. The fundamental theorem of calculus just says, look, if we'll take this, if this thing right here is the derivative, right? Then we can go in and find out what its antiderivative is and evaluate it at f of b and f of a. So one of those videos we did where we talked about, finding the area and how the area was the same as the change in y values, right? That's really what we're doing here. So to use the fundamental theorem of calculus, we're going to take the antiderivative, right? Or we're going to integrate, take the antiderivative or integrate. We're going to plug the top number in, sorry about that. We're going to plug the bottom in. And when I say plug the top and bottom in, what I mean is here's the top number, here's the bottom number, and subtract. That's really all we're going to do to figure out what this thing's equal to. Okay, so this thing is going to equal the antiderivative evaluated at the top minus the bottom. Okay, so let's go in and we'll look in the next slide to see how we actually do that. So there's a rule that says if we have something to the n power, the antiderivative of that is x to the n plus 1 over n plus 1. We did a lot of that when we were talking about the indefinite integral. And so when we do the definite integral, we're going to apply that same rule. Let's talk about how we go from here to this thing right here first, okay? So I'm going to take t to the second power. I'm going to add 1 to its exponent, and I'm going to put that new exponent on the bottom. So that's where we get t to the third over 3. And then 4, so it's not exactly obvious, but 4 is the same as 4 times t to the 0. And if I add 1 and put that on the bottom there, then I get 4t. All right, so going in and looking at, all right, well, what do I do now that I've got that antiderivative? Okay, so now that I have that antiderivative, I'm going to go in and say, well, I'm plugging in 2, right? You'll notice there's a little bitty line, and it's kind of hard to see right here. When I write this, I put t to the third over 3 minus 4t, and I put a long line right there just because I want to make it obvious. We're going to plug 2 in, right? We plug 2 in for t, and we're going to plug negative 2 in for t. Okay, so going through and evaluating this is where a lot of times we get lost in the order of operations and why is this number negative and why is it positive. So 2 to the third power is 8, and 8 over 3 is our first value, minus 8, right? 4 times 2. So right here, if I do negative 2 to the third power, it's negative 2 times negative 2 times negative 2, right? This gives me a negative 8 over 3. Excuse me. Here I have a negative times a negative, which is a positive, and I'm going to go in and distribute that negative so that I can combine all these like terms. So I have 8 thirds and 8 thirds, and then negative 8, negative 8. And remember, when we add fractions or when we subtract fractions, we have to have a common denominator. So if I put 16 over, if I try to change this 16 to something over 3, it's going to be 48 over 3. And when I subtract those, that's where that negative 32 over 3 comes from. Okay? So the big step here, the big new thing was, where on earth, how do we get this right here? And that's where we did that antiderivative. Okay? It's what we talked a lot about in the first half of this particular module. Notice that we don't have the plus c. We don't need the plus c anymore because we have a definite integral. Here's another one where we're using the second fundamental theorem of calculus, and you can see how we took the antiderivative right here. So I'll leave you to work through this one on your own, and we'll focus on a problem that looks like this. Okay, so if I said let's evaluate, right? Evaluate. Normally, when we say evaluate in math, we want the answer to be a particular number, and so in this case, when I evaluate, I'm going to take the antiderivative of x to the third, right? So I'm adding 1 and putting that on the bottom. Minus 6, right? 2 plus 1, and I put that on the bottom. Plus 4x to the 1 plus 1, and I put that on the bottom. Okay, so this is where we're getting x to the fourth over 4, right? So instead of saying x to the fourth over 4, we have in the PowerPoint 1/4 x to the 4. Notice that 2 plus 1 is 3, and 3 and 6 cancel and leave 2, right? So this is 2x to the third. And the same thing here, right? 1 plus 1 is 2, and the 2 and the 4 cancel, and we get 2x to the second. I would prefer to have 1 and 0 written like this so that it's really obvious to me what I'm doing. I'm plugging 1 in, and then I plug 0 in. Of course, we're going to get 0 right here. All of these terms will give me 0, and 1/4 minus 0 is just 1/4. So really the tricky thing is it's normally not finding the antiderivative. Normally the tricky thing is with this negative, making sure you put the correct value in the right place. So what I get from plugging in the top number goes first, and what I get from plugging in the bottom number goes second. So here's an interesting problem, and usually what happens with this one is we have a hard time finding the antiderivative. I'm going to rewrite this problem so that it looks like this. Now, there are two things going on here. First, where on earth does the 1/3 come from? So the cubed root, right, is what we're changing to the 1/3, right? Next, how on earth did we get the negative? Okay, so I'm going to move anything that's on the bottom, I move that to the top, and that exponent becomes negative. So now when I take that antiderivative, I'm going to have x to the negative 1/3 plus 3/3 over negative 1/3 plus 3/3 evaluated from 1 to 8. Here's what that would look like. 8 to the 2/3 over 2/3 minus 1 to the 2/3 over 2/3. See how that plays out here. So I have 3/2. All right, so the 3/2 comes from this. When we do 8 to the 2/3 over 2/3, right? Remember that when I'm dividing by a fraction, I'm going to multiply by the reciprocal. So that's where that 3/2 comes from. Same thing with this 3/2 over here. Now, let's talk about how to evaluate 8 to the 2/3. So we're going to take 8 to the 2/3 and rewrite it as the cubed root of 8 squared. If I take 8 and break it up, I can find its cubed root like so. So the cubed root of 8 is 2, and when I do 2 to the second, I get 4. And then 1 to any power is just going to be 1. 3/2 times 4, right? That's 6 minus 3/2. Again, I'm going to get a common denominator, which would be 12 over 2 minus 3 over 2, which we all know is 9 over 2, and it does not have a pretty decimal. It's 4.5, right? So it's not an integer. We just leave it 9 over 2. Here's another problem where we have some rational exponents. I'll leave this one for you to look at on your own. This one, 3t to the negative 1/2, works very, very similar to the one we just finished. This is one that I thought maybe we could look at together right here. Okay, so x minus 1 over the square root of x dx. This integral is really complicated if you don't pick up on this one little thing. I can change this fraction so that it is one fraction that looks like this. Now, the second term, I think we can all agree is going to be x to the negative 1/2. And this is just based on what we've been doing with our other problems. Okay, so I call this square root of x, I call that x to the 1/2, and I move it to the top so that it becomes a negative 1/2. Now, we really need to focus on this thing, x over the square root of x. So x to the 1, right, could be x to the 2 over 2. Now you're thinking, why on earth would I do that? Well, if I have x to the 2 over 2 and I divide by the square root of x, that's really dividing by x to the 1/2. And when I divide, I subtract those exponents. So I can rewrite this first fraction as the square root of x, or x to the 1/2. So there's a lot of algebra that goes on with this problem, and breaking that up into something that I can work with. We've got that detailed for you right here. The PowerPoint just doesn't go into as much detail as I did with, how do you get from here to here? And you can see that's played out right here where I subtract those exponents. So I need to go in and take the antiderivative, right? I'm going to take the antiderivative of x to the 1/2. So the antiderivative of x to the 1/2 looks like this, minus x to the negative 1/2 plus 2 over 2. So I'm adding 2 over 2 because that's a fancy way of adding 1. Here's what my antiderivative looks like. X to the 3/2 power over 3/2 minus x to the 1/2 power over 1/2. So we talked about this a few minutes ago. We can change this to 2/3 x to the 3/2 minus 2, that's not very pretty there, minus 2 x to the 1/2, okay? And that's what we show you in this next slide here. Notice we're going to plug in 9 and 1. So I've got 9 to the 3/2 power and 1 to the 3/2 power. I like 1 to the 3/2 power. It's just going to be 1. So this guy right here is 2/3 minus 2. Let's talk about how to evaluate 9 to the 3/2 power. The number on the outside indicates what that index is right here. So in this case, that index would be 2. And that really means just take the square root of 9. The square root of 9 we know is 3. And then I have to do 3 to the 3rd power. So that guy goes right here. 3 to the 3rd power is 27. And you can see 27's here. And then right here, this is minus 2 times 9 to the 1/2. So 9 to the 1/2 is the square root of 9. Right, so I'm just going to have 2 times 3. So 3 will go into 27 9 times, and 9 times 2 is 18. 18 minus 6 minus 2/3 plus 2. Don't forget you have to distribute that negative. If we combine our numbers, we wind up with 40 over 3. Here's a problem that is just like the one that we finished talking about just then. Take a look at it, see what you think. You can walk through that one on your own. This is another one that's very, very similar. There's a negative exponent thrown in there that's a little different. My hope is that you're able to, between the PowerPoint and the video and what we have for you in Newton, you're able to go in and navigate some of these problems, okay? So remember, when we're doing this thing right here, the integral of u to the n du, or x to the n, we have u to the n plus 1 over n plus 1 plus c. So this is an indefinite integral. And when I have that indefinite integral, I have to have the plus c. With the problems we just finished working, we're finding the definite integral. Okay, so when we do our problems, we're going to have u to the n plus 1 over n plus 1. And we're going to plug that a and b value in and subtract. All right, and that's really what the second part of the fundamental theorem of calculus is for, is to help us identify How do we actually go in and evaluate this? What's the math behind getting that answer? Take a look at some of these problems. We're going to do a whole lot with the fundamental theorem of calculus over the next couple of weeks, and that should wrap the course up for you and get you ready to go into Cal 2 for the next course in the sequence.